Time for the good stuff. Organic reactions. Reactions, not just acid-base proton transfer, but changing what's happening on the carbon chain, right? Yeah, I'm removing an H can make changes, but we're talking about changing functional groups or extending the carbon chain. That's pretty exciting. So why is this important? Big picture down the road, chemists are asked to make, design, engineer natural products. Take this synthesis, for example. Let's say you're told, hey, chemist or engineer of synthetic materials, go make that, remdesivir or something like it, some antiviral agent to help us all. Now, what a chemist needs to do, an organic chemist needs to say, okay, well, what functional groups are there? And do I know what bonds are the most easy to have made this from? How could I put this together? What pieces could I have used? So you kind of think back, and you could see it came, this is from Gilead Sciences, by the way. You can see it started with some really small, simple pieces, and it built up to that. And look at all those reactions. That took a lot of planning. Look what's over the arrow. So these things looks a little foreign right now, but they're always going to list solvent, conditions. So time sometimes is listed, but definitely temperature is usually specified. That means room temperature, RT. Usually we use units of Celsius. We write times in our lab notebook at the very least for this reason. Solvent is shown because these might be solids. They very likely are. Solids don't mix real well and start reacting, so you have to dissolve them in a solvent, not water, because these are not as polar as water usually. So it's something else that is organic and we'll dissolve them. So we'll go over a list of suitable solvents. So there's a lot to consider. There's the conditions, there's the reactants, then there's why would they react, the how. So we're going to go over some terminology. I wanted to show you a picture of that sort of typical organic reaction happening, right? And so what's going on in there is when you start, you have your two solids, possibly, maybe two liquids, but sometimes you need a solvent to be added. And then this is a round bottom flask, sand there to help heat it evenly. Heating mantle. So that's the heating element, gets heated, transfers the heat to the sand warms up and transfers the heat gently and uniformly to the contents of the round bottom flask. Sand is only added because this diameter doesn't match that diameter. If it was snug, you wouldn't have to do that. The clamp is around the neck of the flask. This is a ground glass joint. Notice the outer diameter is smaller than the inner diameter, and the inner diameter fits very perfectly and snugly with this other glassware piece. It's called a condenser. Why do we need that? Notice the condensation happening there, right? So it's because we're heating. Liquid can turn to vapor. We don't want to lose it all. Let that turn into a big black burnt char at the bottom. So instead of losing all our liquid, we cool it with some water coming in and it condenses back down. So by the end of this, we're going to learn this reaction. A little visual here. So you might put these two in there. Those might be your two reactants like A and B. So it could be something, this could be as simple as methyl iodide with bromide ion, like sodium bromide, potassium bromide that's been ionized in solution, floating around. Now, if this finds that carbon, which has a delta plus on it, could attack and kick that off and replace it. So eventually, if you leave it long enough, that's what we have. Lots of those. We replaced a purple with a red. Replace. We could also say substitute. Substitution. That's the concept behind substitution is simple, but understanding the what and why and how is going to take some digging deeper. And in order to do that, we are going to brace yourself for get comfy, get some definitions down. Not my favorite thing to do, but it's a necessary evil because we can't start just talking about it like we knew this forever. I know that some of this will be familiar if you're lucky. You might have had this sprinkled throughout general chemistry, but we'll just assume it's not. Speed me up if you have to, but we gotta talk the same talk before we can start drawing out structures and get into business. So just to put this in perspective, now that we're in the organic chemistry reaction realm, and I'm not discounting acids and bases, they're just their own category of the Bronsted-Lowry acids and bases, right? We're talking about like H+ transferring, proton transfers. But we're going to get to some more exciting ones that you hadn't seen yet. That's part of what makes them more exciting. They're all necessary and important. So you can put them in one of these three categories. Maybe they changed the carbon framework. So the carbons are now in a ring, or they are longer or shorter. All right, so you could add carbons, lose them. You could rearrange them, right? Or we could do what's called functional group interconversion. We change the functional group. We swap out one group for another. Substitution. But we will also change a group without taking it. So we could oxidize it or reduce it, but we didn't actually take that group away from the molecule. We can also do something called addition or elimination. All right, so those will all come into focus soon, but today the star is substitution. Okay. All right, so features to consider. Reactants. We're going to use that word, reactants. We're going to use sometimes some nicknames, aka starting materials, SM. We're going to talk about them so often they have another abbreviation, SM is starting materials. This includes reagents. So this is another term. Well, reagents, are they a reactant? Yes. Is a reactant a starting material? Not usually. So it includes reagents and starting materials. Reagents are things that you, like if you need to add an acid to make the reaction happen, but you didn't collect the acid at the end, you weren't trying to. Or the acid got turned into a base, but you really cared about the organic piece, right? So the reagent is really like the jar of stuff that helps facilitate the reaction, but the main carbon framework is the starting material that was really important to us. Products. Okay, so we are going to make you cringe in the beginning because you've been taught to carefully, meticulously balance your equations. And we're going to practically throw that out the window. We will pay attention to it when it matters, but we really care about that organic product. Do you think we care about isolating some phosphate, triphenylphosphine oxide that was produced along with remdesivir? No, but it was a product, so I'm not balancing that equation. We only do that when it matters, when we're trying to decide how much of something we need to use in the lab. Okay, so I'll write that here. Often, inorganic product is ignored. The other time I intentionally draw the inorganic product is if it clarifies how the reaction happened. But if we didn't really need to write it all out, we probably won't. Mechanism. Talked about this with acid base. It's those curly arrows. That's going to be huge. Curved arrows show the flow of electrons. This is the how. Conditions. So we've mentioned temperature. It could be room temperature, which is just written RT, just means we didn't add any additional heat. It could be an ice bath. It could be colder. So it could be a type of ice bath that's listed there. Sometimes there's a specific pressure, not really in most of the reactions we cover in this class, but light, wavelength of light is the energy source as opposed to heat. So I'll put wavelength. Even pH, whether it's acidic or basic conditions, that's another one to consider. Now solvents, what do we need a solvent for? It's going to dissolve solutes. That's what solvents do. What are the solutes? Our reactants. Allows thorough mixing. Why do we need thorough mixing? Because we need them to bump into each other. Bumping into each other causes collisions, which allow bonds to form. Thorough mixing. Okay, now sterics and electronics, big ones. So a lot of this was, what do we do to set it up? How do we set it up? This is kind of the why. Why do the reactions happen? It's one of two reasons or a combination of both, usually, when we simplify it. So sterics has to do with bulkiness, size effects. So if it's too bulky, not usually too small, that's not usually an issue. It just means it's unreactive. We say that has steric hindrance. Steric hindrance. It stops the reaction from happening. The steric bulk hinders the reaction. Okay, because it needs to get in there and collide into the atom to react. If it's too small, that's not an issue. It gets in there. If it's too big, it doesn't. No reaction. Okay. The other effect at play is electronics. Delta pluses, delta minuses. Are they attracted to each other? Full pluses, full minuses, right? So charge effects. Anything relating to charge distribution. So we'll be looking at the simple idea of plus attract and delta plus attracted to minus or delta minus, right? And while we're trying to understand what's going on, we'll sometimes use data to help back that up and or explore, look up the data, see what it says. And so that we're talking about thermodynamics at this point. So some of the parameters you want to be comfortable with is Gibbs free energy, enthalpy of reactions. There's a lot of H's out there, but it's specifically enthalpy. Delta T, that's temperature, and delta S, entropy. Okay, so we will not go into this huge of detail with thermodynamics and general chem. They have a whole chapter on it. We're just kind of taking these consequences of it to help explain what's going on. A couple other terms that I want to get out of the way. And then we're going to do a little review of what's, like I said, some of this was from general chemistry, but I'm going to point out what you might have seen from there before we get to the new reaction, which is coming soon. So we have this idea of stereoselectivity or stereospecificity, kind of used interchangeably, not exactly, but we're not going to harp on that too much. But the idea is that if we see a reaction preferential formation, so it's selective, something's selective, it's snobby, right? It's preferential. So it prefers something related to stereo, prefers one stereoisomer over the other, preferential formation of one stereoisomer over the other. Why does that happen? That's what we get into. Maybe the mechanism only happens a certain way. Maybe the reactant's shaped a certain way. Maybe the reactant has this one reactant in question has a specific charge distribution, right? So then we'd say that particular reaction is selective for that, the formation of that particular product. Regioselectivity, preferential formation of one regioisomer, constitutional isomer. So one regioisomer over another. So in other words, at all of the sites that bonding can happen, there is one site that's preferred over the other. So in other words, cyclohexane has 6 carbons. If there's one that keeps getting attacked and the others aren't, we want to say, well, what's attached to that? Why does it like that one so much? Why is it exhibiting such regioselectivity? So those are the questions we like to ask. So just some equations that will be brought up very casually, but they have a lot more depth to them than it appears in the way that we're going to use them, to be honest. Gibbs free energy, so delta G equals delta H minus T delta S. We see it in here, but we also see it related, the standard Gibbs free energy, to the equilibrium constant. So we'll keep that in mind, where the equilibrium constant, as we reminded ourselves back from acid-base sort of chemistry, is it's the concentration of products over the concentration of reactants. And then this one we do spend a lot more time on the rate law. So the rate is this rate constant times any reactant. So if you have several of them, they all get multiplied out here. So whatever reactants you have, they get included. And because we care about kind of what we want, usually if we're going to plan something, we want that reaction to happen. So we want to know, not waste our time, many hours in materials in the lab. We have to spend a lot of time on paper planning out a synthesis so that it's not hundreds, thousands, millions of dollars and then a lost job over wasted resources when it could have been planned theoretically. So when we can figure out if a reaction's preferred, you're not going to go into the lab and do a reaction that's not spontaneous. If it has a precedence for being preferred, or we can calculate that it should be preferred, model that it should be preferred using something similar to Spartan, then go ahead, go use the materials in the lab, right? All right, so we are going to take advantage of a reaction we already know to learn the new one. Good old-fashioned acid-base. You know what happens here. Lone pair, follow along with me, takes that H, that proton. The lone pair is attracted to it. That full minus is attracted to that delta plus. H must relinquish that bonding pair and leave it with chloride. Okay, so what does that look like? That looks like HOH, no longer hydroxide. Lost a lone pair, plus, and so that's this H here, right? And this lone pair. And chlorine is now all alone. We've been calling these acids and bases. HCl we know is an acid, we know hydroxide's a base, but we need to start transferring our terminology more broadly to electrophile and nucleophile. Why? Because if we could see other reactions as parallel to this, it will not feel like a jumbled memorization set of information, which is really actually impossible to make this all memorization. It needs to be kind of worked out. So knowing that something acts as an acid or base means you also know it can react as a nucleophile or electrophile. And I've heard a lot of students say, by the time they kind of get the aha moment, closer to the end of the class, maybe even maybe at the end of Organic 2, they'll say, every reaction is an acid-base reaction. Kind of is. It's about who's willing to give electrons to share and who's willing to accept them, right? And acid-base, it's just proton transfer. But now we're talking about Lewis acids and bases, which is more generic about electron sharing. So the Lewis acid is here. It matches the Bronsted-Lowry acid. It's just the Bronsted-Lowry is a specific type of acid, right? It's the one that specifically has an H to give, and this is a Lewis base. Okay, so we did that. Nucleophile. Who's the nucleophile? Nucleophile means loves the nucleus. So negative would love the nucleus, right? So I'm going to abbreviate because we use this term so much. This is our nucleophile. And electrophile, I'm going to abbreviate U+. That's convenient because that's our electrophile right there. Okay, so now let's make one small change. We're not going to do an acid-base reaction with this one little change. Do you see what I changed there? Instead of the H getting attacked, who has the delta plus? A carbon. It's very exciting because we're going to make a carbon bond. So, same rules dictate it. The negative is attracted to the delta plus on the carbon. Carbon already has a full octet, so it says you're not going to bond with me unless I let go of chloride, which it does. So we can assume, by the way, that a reaction happens unless we have data to prove or to suggest otherwise. What happened to the chloride? It's by itself now, just like the previous example. Okay, so let's label everything. Nucleophile, electrophile, right? Our electrophile was an alkyl chloride, and when we were done, we made an alcohol. We changed functional groups. We traded out the chlorine for an OH. This is more complex than just where the H went. It's where the whole new group, the nucleophile, everything attached to it, that nucleophile and its H came along, attacked there, and it let go of this group. This is called substitution because we substituted a hydroxy group for a chloride group. Okay, so a couple other terms. When chloride left, not everything will leave. Some things will say, I'm just fine right here, thank you very much. So, but chloride was willing to leave. That's something special. So this is called a leaving group, LG. That's going to be an important feature of a substitution reaction. You can't do it unless you have a group that's willing to leave. What made it willing to leave. Cario, same rules. It's a relatively stable anion. The consequence of it leaving is gaining charge. But it's a relatively stable anion, so it can leave. So leaving groups have that in common. When they leave, they're okay with the charge they generate, or the change in the charge. Okay, rate law. Remember, rate equals K reactants. K times concentration of reactants. How many reactants do we have? We have 2. So we have K times hydroxide times methyl chloride. What does that mean? They each have an exponent of 1. Remember this, perhaps? What is the order? If it was only one reactant, it'd be first order. 2 of them, we now have second order. Okay, so both of those determine the rate of reaction because they're included in the rate law. So in other words, how many different types of molecules are included in the rate law? 2. This one and this one. They react with each other in order to produce, at the same time, in order to produce the products. So they determine the rate. Sorry if I left that blocked. I'll put that here for a second. Okay, so substitution. So far what we've learned is this substitution reaction is second order. We're going to write down SN for its nickname 2, SN2, substitution 2, second order substitution. I'm going to flesh that out on the next page, but just in case you went back to these notes, I wanted you to also see it here. So remember, it's a substitution because we traded one group out for another. And it's SN2, second order substitution, because it has 2 reactants participating at the same time. So the real name, as opposed to that short SN2, when you look in your textbook, is bimolecular. 2 molecules. Nucleophilic. So nucleophile attacks the electrophile, in other words. Nucleophile replaced something in the electrophile. Substitution. Substitution. So now that should make more sense, that nickname. Nucleophilic, so substitution S, nucleophilic N, bimolecular 2. And so it usually has that little n to kind of, that's capitalized but subscripted almost at the same time, just to kind of make it clear it's different. So it's SN2 basically. So some things we might ask how we would understand the rate law. We're not going to go like you might have memories of looking in the appendix of their general chemistry book and looking up numbers and calculating rates. Instead, we don't have time for that. We've got to just make decisions like how fast does this reaction go, or what's the consequence of changing a parameter in this reaction. So we take the rate law and we just talk about relative changes, right? So in other words, a really common question is something like this. What would happen to the rate if we doubled the concentration of hydroxide? I'm writing the rate law again right here. Hydroxide times MECl. They're both there. So if we double this, we double the whole rate. What happens if we half the concentration of methylene chloride? Half it, right? You divide one thing by 2, you're dividing the other thing by 2, so half. Okay, so luckily for everybody, that's as complicated as it gets, is 2. And so just to kind of think about being out on the freeway or something, if there's a reaction, or excuse me, accident, 2 cars come together, sometimes there's a pileup, a multi-car pileup, right? But did that happen simultaneously? No. You either have a car that got hit, or you had 2 cars that were traveling the same trajectory at the same time and hit each other, right? That third car, even if it's that it starts to land into, even if it's a nanosecond later, it's not the same time. It's because one of those Two hit before the other one did. So we will not have a tri-molecular rate law, in other words. Not going to happen. So lucky for us, we're sticking to second order or first order. Those are our options. And we'll get to first order later. But right now we're going to look at second order. Okay, so far we've worked out quite a bit. So I'm redrawing this with the computer style here, so it's a little cleaner. Hydroxide, electrons attack the delta plus on that carbon, because that's our electrophile. This is our, this is our nucleophile. This is our electrophile. That means there must be a delta plus right there that negative is attracted to. So our nucleophile attacks our electrophile. Then we have our products. And sometimes, because this is not organic, this has the organic R group we were looking for, this might not even be shown. We'll get used to it. So in other words, we're not, that's why we don't take a lot of time to balance reactions. This got sort of marked out, but that said collision. But another, I'll just make it say POW. You know, those comic book things. They collide, and then they come away different. So what we're going to focus on next is what's in the POW. Okay? So that's our next focus. What's in the POW? What's going on in that mysterious thing that allowed them to collide and come apart different? So stick with me, keep watching, or take a break and come back. See you soon.